Thank you so much for joining us for our WaterWise Brown Bag Seminar. Today's topic is citizen science and the quality of harvested rainwater. Can you all see my slide presentation? Okay, great. So just to introduce myself, my name is Alex. I'm the WaterWise Youth Program Coordinator. Today, we're going to be hearing from Dr. Monica Ramírez Andreotta, and she is an assistant professor of soil, water, and environmental science with a joint appointment in the Mellon Enid Zuckerman College of Public Health's Division of Community, Environment, and Policy at the University of Arizona. Additionally, Dr. Ramírez Andreotta is the PI of the University of Arizona Superfund Research Program's Research Translation Corps. She also heads the Ramírez Andreotta Integrated Environmental Science and Health Risk Lab. So the lab's research programs revolve around developing a fundamental understanding of the fate and transport of contaminants in the environment with a primary focus on plant soil systems and phytotechnologies to improve soil and air quality. Dr. Ramírez and her team are committed to serving the community and building citizen science programs, which we'll be talking about today, to increase public participation in environmental health research, developing low-cost environmental monitoring tools to improve exposure estimates, and designing effective risk communication and data report back strategies to improve environmental health literacy. Dr. Ramírez Andreotta is dedicated and has been successful in reaching underserved populations. Her lab functions under the philosophy that in order to successfully engage communities and students, it is essential to address critical environmental health problems identified by the community and then work collaboratively through the problem solving and research process. Her commitment to this kind of collaborative problem solving is reflected in the title of this talk, which she requested be named Citizen or Community Science, to reiterate how citizens were involved in the gathering of the data that we'll be talking about today. And with that, I hand things off to Dr. Ramírez Andreotta.
So welcome. Today I'm going to be talking about Project Harvest and just giving an overview of results. Thank you so much for having me today and for the invitation, Alex. It's exciting to be talking to members of Cochise County. It's been a little bit. I did do 2015, 2016, based on a needs assessment. They were members of your county who participated in Garden Roots, where they collected soil, water, and some plant samples. The data was reported back and shared. Primarily, majority of the participants were from the Bisbee and Wilcox areas and Sierra Vista. But so it'd be great to see where everyone's from, Livia, as we move along through this presentation. So just to begin, right, is we want to explicitly acknowledge that the University of Arizona is on the lands and territories of indigenous peoples. Today, Arizona is home to 22 federally recognized tribes, with Tucson being home to the Tono O'odham and the Yaqui. We also, are a Hispanic serving institution. So this is where the University of Arizona has been recognized for its high number of students who are identifying as Hispanic, Latino, Latinx. And in 2019, the U of A received the Seal of Excelencia for Latino Student Success, which we're very proud of. I want to acknowledge these because I grew up actually in Tucson, Arizona, which is along the US-Mexico border region. And I'm second generation Mexican American and very proud of where I'm from and happy to be serving my community. All right, let's just jump right in to say that all of you and others across the state and actually globally are trying to do the right thing. Right, so some of you might be growing your own foods, and you might be doing this because you want to have access to high quality vegetables and food products. You want to reduce your carbon footprint. You want to address food deserts, and you're sharing your crops and vegetables. Also, you might be harvesting rainwater, right? So you're trying to contribute to reducing our water footprint, reducing our dependency on the public water supply or your private well supply. And so you're harvesting rainwater as a form of conservation and as an environmental steward. So one of the things that gets me really riled up, and maybe gets all of you riled up as well, is when pollution interferes with these amazing acts. right? So we know that gardens can serve as a public health prevention and intervention to address access and nutritional needs, and also provide green space and to improve mental health. We know the benefits of harvesting rainwater are critical for to irrigate shade trees, perhaps, right? Other crops and fruits and vegetables that you might be growing on your land. Specifically within Tucson, Arizona, in the southern metropolitan area, the city of Tucson has offered a rebate program, which is a rebate to do passive or active rainwater harvesting. One of the things that the city of Tucson, as well as the collaborating organization Sonoran Environmental Research Institute, based in Tucson, Arizona, acknowledged was that those who were getting the rebate and building harvesting rain water systems were those who were higher income and in more affluent neighborhoods in the Tucson area. And when we looked at who was getting these systems and rebates, we saw that pattern. But the other thing was that the ones who needed it and who were suffering from heat island effect, right, lack of tree canopy, were those who were living in what we call an environmental justice space, or who are considered low income, living in proximity to pollution, and have social vulnerabilities. This could also be the case for rural communities that might be living near sources of pollution like toxic release inventory sites, resource extraction, or mining. I bring all of this up because people are trying to do the right thing. However, sometimes pollution can get in the way of that. And I also bring up the issue of access and justice, as I gave the example with the city of Tucson, and looking at a community that needs more green tree canopy, right, for shading purposes, to reduce their electric bill, to address heat stress due to climate change challenges. And so I want to acknowledge right from the beginning that you're talking to someone who's prompted to create action for structural change. So what does structural change mean? It means that you're trying to affect the macro or meso level of determinants of health. So you're trying to look at, like, how does economic and zoning and environmental policy, like, how can we change those things to improve health and environmental health, right? So we're looking to create changes at these zoning, economic, political levels, the built environment, public health, public service provisions, and environmental policy enforcement, all with the notion to protect environmental health that each and every one of us can benefit from. When we think about these projects, we state to be intentional and to think about a co-created, co-designing approach to the science. And one way to do that is you can think about and look at this listing of the steps in research, and you can think about the level of contribution and work that and the work that community members can do that we can all do together. And so I'm going to go through some of these steps throughout this presentation. I also want to acknowledge that when we look in the literature, we also, because of the high level of going back here of interpreting data, disseminating results, we use an equity-centered community design approach where you can see here that there's some overlap into these steps of the scientific study. And we can see here we had overlap in the way we shared the data and co-generated. So to get started, you can see this is a big team. These are promotoras, or community health workers that reside in the communities in which we're part of Project Harvest. These are a mixture of team members and students. So a big shout out to Shayna Sandhouse, who is the program manager and is now a lead evaluator for the Virginia Museum of Arts in Richmond. Big shout out to external evaluator Salen Buxner, and team members you see here: Rob Root, Leaf Abriel, Aminata Kilongo, Jean McLean, and students who just recently graduated, AJ. So everyone's doing great work here, and Flor Sandoval from the Sonoran Environmental Research Institute. And so I just want to give a big shout out to the big team doing this work. All right, so like I started to talk about, right, families are conserving rainwater to conserve water, reduce heat island effect, increase green spaces, irrigate gardens. I have reduced heat island effect listed twice because I'm so passionate about it. Apologies for that error. And so you can see here, like, these are some images from Tucson, Arizona, and then these are images from areas neighboring, an image from a community neighboring a legacy mining site. And so the questions that were derived from community needs assessments, ongoing interactions with the community boards or and non-governmental organizations were, are there pollutants in harvested rainwater? And can I use the harvested rainwater for my garden? And so this really came up in Garden Roots, a project that I briefly mentioned earlier, where people are, again, are trying to do the right thing. And they're like, hey, I'm harvesting rainwater. How can I use this? Like, I've been told not to use it on my garden, you know, but is that the case? And so forth. And is a really good question. And so we together, this informed the study. So we looked at, right, what is the quality of the harvested rainwater? What's the quality of the soil irrigated with harvested rainwater? And we compared that to soil that's not irrigated with harvested rainwater. And we also looked at plants that had been receiving harvested rainwater throughout the duration of the project. And within this, as you saw with the diversity of team members, right? So Aminata Kilongo and Jean McLean are environmental microbiologists. Rob Root is a geochemist. Leif Abriel is an organic chemist. And then Sandlin Buxner is our evaluator coming from College of Education. I'm an environmental health scientist, right? Doing exposure science work and communication efforts. Combined with the community questions, we all came together to look at and answer what is in the harvested rainwater soils and plants. And we looked at a suite of metalloids, pesticides, industrial compounds, and microbial indicators. These are just some images of how people would set up their, so this is looking at soils not irrigated with rainwater, these receiving that harvested rainwater, and then just some other examples from around the communities. Another big step is gathering information and resources. And so you can see here that we did informal gatherings to identify interested community members. We have continue to have engagement, specifically needs assessments were conducted in the rural communities. And you can see here that we had promotoras, or community health workers, were identified and trained in each community. That we had Aviva, Imelda, Teresa, and Palmira, who worked in Tucson, Arizona, Lisa Ochoa for Hayden Winkleman, Margaret Dewey for Dewey Humboldt, and Miriam Jones for the Globe Miami area. And the reason why we worked with promotoras or community health workers is because they're individuals who share similar backgrounds or life experiences. And so they're sharing the information with their peers or the community in which they are from. And so this works out what we call peer education, or the empowerment education model. So we trained all the promotoras, and then the promotoras go and train the families. If we look here, this is a list of everything that we, based on community location, community concern, a literature review, an analysis of existing national data sets, we selected the contaminants that you see listed here. As you see for microbial, these are both indicators. And then for inorganic, you see these list of metals, or arsenic is a metalloid, well, heavy metals listed here, and a mixture of industrial and pesticide compounds. Also, so everything you see here listed was tested for in the lab, but we also created do-it-yourself tests for indicators for total coliform and E. coli and arsenic. All right, so who did we engage? So I'll show you a couple maps to follow, but we had on average throughout the 2.5 years of the project, we had to end early due to COVID-19. We had 148 participants, and over 50% of the participants were from low-income households, did not have a college degree, identified as a person of color, and almost 50% were from rural communities, and 25% spoke Spanish as their dominant language. I highlight this here because you can imagine the levels of intersectionality and the different life experiences people were bringing to the table as participants and colleagues in this work. I'd also like to acknowledge that this is not traditional of citizen science. Citizen science as a whole has been critiqued for only reaching those who are from high income, educated, and or white. And that's been a critique of the field. And so because of the design, right, the co-created community science design employed here in collaborating with the Sonoran Environmental Research Institute and having promotoras in each community, as well as myself being a cultural knowledge broker, we have been able to engage non-traditional participants. These are the communities that we worked. You can see here, Dewey Humboldt is a legacy mining site. This community is sandwiched between two sources of pollution, the mine tailing pile, as well as the former smelter. Let me go back. You see here, you have Hayden Winkelman, which is known as a Superfund alternative approach, and has currently the smelter is not active, but at this beginning, when the study started, it was. But here's the town and the smelter here, and there's a school right at the bottom, right around this area. And so you can, and here you see Globe Miami with a variety of open pit mines. And then Tucson has what we call 9 state, federal, or Department of Defense cleanup sites within the vicinity and targeted area. And this is a map from the Toxic Release Inventory site, which I can answer any questions about. What I'm showing now, you see that there's a year. This is showing the beginning of the partnerships in these communities. So I've been working in the Tucson, Southern Metropolitan Tucson area since 2006 with SERI, and also working in the Dewey Humboldt area since 2008, and then in Globe Miami and Hayden Winkelman starting in 2016. And then the number you see here is the number of participants that throughout the project. All right, so here's that breakdown. We had 53% of families were urban, 47 rural. Here you can see that almost, again, just that breakdown, like urban represented here with Tucson and participants from the other communities. We see here that going back to the community members' role and what co-generating the work, we see the steps in research. And so participants decided where to collect soil samples, what vegetables they wanted to grow and submit for analysis. They collected samples, especially if they were doing the DIY. They collected the samples, had a result, and would report it back to the university. And they also recorded observations in a lab journal. And so this is just showing that community members' sense of control and participation in the data collection. I'm just going to go into a little bit of detail here. So for the do-it-yourself, let's see if I have that. Okay. So do-it-yourself is exactly as it stated. Participants would be given a kit, keeping track of time, would be given a kit to measure sulfur-reducing bacteria to be an indicator of total coliform. And they would conduct that experiment at a time that worked for them based on, I'll go back to the timeline, when it were at a time that was that they had time for. And then the lab was something where they were given all the vials and bottles, and they would collect the sample and send that to the lab, versus the DIY, they would conduct the experiment at their home and then report the results to us. So as part of the learning research, so this is funded from the National Science Foundation and is an advancing informal science learning grant. One of the things we wanted to look at is, were there any differences in learning outcomes based on kit type? And so in the very beginning, we randomly selected participants who would receive the DIY kit and the other half would receive lab. And then they would switch kits between year 1 and 2. And year 3, they chose their kit. For year 3, the majority of people chose lab or were assigned a lab kit if they did not provide their preference. And a handful decided to do both. So I just talked about these methodologies. Like I said, for lab, you collected, the participant or families would collect that sample and submit it to the lab for analyses. And for DIY, they would be looking at a sulfur-reducing bacteria as an indicator of total coliform. And so they would collect the rainwater, add some packets, and then maintain these 5 vials in a temperature, as best they could, temperature controlled space for a week. And then for arsenic, this is where they would collect the sample, add some chemicals to that, and then they would get a reading after doing some intermittent swirling for about an hour to then compare it to a strip to see what the estimated arsenic concentration was in that water. Oops. All right, so we had this, you can see here's a little bit of this table showing that the project went from 2017 to 2020. And we bracketed the major rain events, the 2 major precipitation periods in the Southwest United States. So that would be the beginning and end of the monsoon and beginning and end of winter rains. And these dates that you see listed here, these timeframes were informed from historical data from the National Weather Service. You can see here that we had to cancel the last monsoon samplings due to COVID-19. Because of our high level of engagement and the interaction between the families and the promotoras, we did not want to risk any exposure in that space. We also administered a home description survey to get some information about the infrastructure. So we asked questions about the home and roof, the rainwater harvesting infrastructure itself, their perceived or known sources of nearby pollution, gardening activities, and potential routes of contamination. These were administered by promotoras, either in English or Spanish, and could be easily done on a phone or a tablet, or were done on paper. Some of the things you can see here is looking at how do you currently use your rainwater. We see that the majority are using it for garden, trees, and landscaping. However, we do have a little bit of people trying to drink it, using it to fill swimming pools, bathing, and dishwashing. If we look at what your roof is made of, we can see that we got a variety of different roofs from the 4 participating communities. And you can see that around, we had this flat built up roof with reflective coating being around 29%. When the majority of cisterns were made out of, here you can see plastic, followed by not answering, and then also giving us metal. The learning research, which I won't spend too much time on, but do want to make you aware that we'd wanted to know if the participation in this level of co-creation led to any changes in knowledge and awareness, skills and self-efficacy to protect health, and community action. And so we measured these in terms of scientific literacy and numeracy, as well as self-efficacy or sense of control, or sense of confidence in learning and doing science, action that was taken. And then as you see for community change, we are still actually currently measuring community building and social engagement. So for today, I'm going to go into some of the nitty-gritty with the data, which is maybe what you're here for, but I want to show you the whole process because this stuff doesn't happen overnight. I'll focus on what you see here in pink. So to begin, let's give a shout out to the students here. We have Jesus Solis Leon and Kunal Palawat, who have been working on the inorganic or the metalloids analysis, along with myself, Director of Project Harvest, Rob Brute, and other students you see listed here. So I'm going to look at arsenic and lead for today. The reason in terms of looking at the metals, just focusing on these two. We can see here some brief descriptions about those contaminants of concern. Arsenic is naturally occurring just as lead. However, it can be released into the environment by mining or smelting in industrial use. When we look at lead, we are concerned about the use of lead in paint. Also used the lead-based solder that was used to connect copper water pipes. Lead also was in gasoline. And so actually it's a ubiquitous or worldwide challenge and issue. The data that I'll be showing today will be reported in micrograms per liter. So this is a measure of how many micrograms of a substance are in a liter of a liquid. And so for comparison, you could imagine that 1 microgram per liter is the same as parts per billion, or this equivalent to a drop of ink in a 15,000 gallon backyard swimming pool. So just want to keep that in your mind as we start looking forward. So one of the things, as you saw from this presentation, is like, how are there contaminants in the water? Like, how do I use it? So to inform us, we look compared to various US, federal, and Arizona state standards. Most participants, right, as you saw, are using the harvest rainwater for watering gardens. And so if we had an exceedance of a standard, we had a one-on-one discussion with participants. So for the sake of today, you'll see that we're looking at surface water, or excuse me, surface water, partial body, surface water, full body. So partial would be like you partially get in this, the water. So this is, imagine if they were like filling up their, so partial body could be like those who are washing their car with the harvested rainwater. Full body could be those who are bathing or swimming in it. Drinking water, drinking it. Livestock and poultry, giving it to animals. And irrigation would be the irrigation of crops. And so what we see here is that I'm highlighting Globe Miami here, but this is just looking at the values, and that we did not have too many exceedances, except for, you can see here, we had some exceedances for the drinking water, livestock and poultry drinking water standard. which is the same as the human US EPA drinking water standard. So you can see these represented here. And for lead, we saw some exceedances for the surface water, full body and partial body, as well as a couple for the drinking water. So but in terms of how people are using it, we only had one sample exceed the irrigation standard and 0 exceed the standard for lead. So one thing that we did is there's this really cool project, we're calling it Skywater, but the University of Wisconsin-Madison has something called the National Atmospheric Deposition Program. And what they've done is they have set up wet and dry deposition monitors or collection devices in different parts of the United States. And so for the state of Arizona, we have the sites that you see here in purple. And so these sites were a comparative value, right? They provided us a comparison of a rainwater sample that did not hit the roof, did not go through any type of water harvesting infrastructure, right? Like a gutter system or downspout, and it was not contained in a cistern. These are samples that were straight from the sky, were collected into a device. So again, this is a background, but also a sample without touching any of the home water harvesting infrastructure. This is an image of what that looks like. And so what I'm going to do here is compare our values, project harvest values, to the Skywater. All right, so here we have arsenic concentration by community. One of the things you can see here, we have Skywater represented in purple. What we see here is that all communities have significantly greater values than Skywater. So these values are at a statistically significant greater concentration than what was observed in the Skywater. We can see here that Tucson, Dewey Humboldt, and Globe Miami are significantly lower than Hayden-Winkelmann. When we look at lead, we see here that Tucson and Hayden had greater values than the Skywater and are significantly greater than the Dewey Humboldt, but then the significance did not hold during a post hoc statistical analysis. So what we're highlighting, the takeaways, is there is an anthropogenic or human influence on the concentrations of arsenic and lead in the harvested rainwater. We saw that all the communities were significantly different than the Skywater on arsenic concentrations, and that there's potentially that for lead, we see this difference in Hayden-Winkelmann and Tucson when compared to Skywater. Some of you, there was a question before that I received about infrastructure, right? Or paints or any type of coatings on roofs and or the cistern that could affect concentrations. Here we looked at whether any, as I previously mentioned in the home description survey, we asked some questions. And so what we saw here in the model is that when the home was built was significantly associated with the arsenic concentration and lead. And the age of the cistern was associated with lead, but the others were not. So when you control for community and time of year, as you saw, we measured at many different times throughout the year for 2.5 years, older homes were associated with more arsenic and lead in the rainwater, and an older cistern tended to have more lead in their rainwater. Even though this is the case, we do want to acknowledge that individual choices about infrastructure generally do not influence contamination. So what does this mean? Like ultimately, which I'll show later on, and hopefully is that we saw differences in the concentration. So I'm going to not show this summary slide right now, that we saw, and I have some of these that I can go through during Q&A, that really your proximity or the further away you were from a source of pollution, a point source, your arsenic and lead concentrations would go down. And I can come back to that. In terms of the microbial, this was led by, so Dr. Moses just recently graduated. And this was informed with the microbiologists Kilongo and McLean. And so here, this is looking at total coliforms, right? And so these are a group of mostly harmless bacteria that can serve as an indicator for fecal contamination, the potential presence of harmful microbes, and they are highly concentrated in the intestines and the fecal matter or poo-poo of warm and cold-blooded animals. E. coli, right, is a type of coliform, and it's naturally found in the fecal matter of warm and cold-blooded animals. It's commonly detected in environmental samples because animals have been going to the bathroom in these environments for centuries, and most types are harmless, but may be associated with foodborne illness. So the reporting of the microbial data will be in most probable number, a method used to estimate the concentration of a viable microorganism in a sample. All right, so we're going to see more data tables here. So right now what you're seeing is that we grouped the brown bar represents all communities together. So that 587 samples. Yellow is Tucson, and rural is the three is Globe Miami, Hayden-Winkelmann, and Dewey-Humboldt together. We can see here that we don't see any significant differences, right, or major differences between the total Tucson or rural. And with E. coli, we see that interestingly, the rural was a little bit lower. However, if we start to incorporate, so let me go back. So if we bring in the rest of the, if we bring in each individual community, again, we can see that there aren't any major differences. However, we just want to highlight the low level in Dewey-Humboldt and the difference between Dewey-Humboldt and the other communities here. If we look at the presence of E. coli and Salmonella in garden soils, we can see here that this is just based on the percentage of positive samples. So we can see that the E. coli, we found E. coli detections were greatest in, when we talk about irrigated soil, were greatest in Tucson and Dewey-Humboldt. And for the non-irrigated, we see here Dewey-Humboldt represented. For Salmonella non-irrigated, we see Hayden having the least percentage of positive samples, but again, we see Dewey-Humboldt being one of the highest ones. And so the reason why we broke things out by community, urban, and rural was just to see if there would be a difference in proximity to wildlife and how population density could affect these values. The major points for the microbial is that fecal indicators are present in both garden soils and harvested rainwater. However, fecal indicators are more common in soil than the harvested rainwater. The animal presence was associated, so in the survey we asked if they had an animal, was associated with total coliform and E. coli. And we want to highlight that since so this is where AJ, right, did a great job of saying, hey, we need to ask how people are irrigating their crops, because if they're irrigating the water from a top-down approach, if they're irrigating from above, that means that the harvested rainwater with the fecal indicators previously shown would be on the surface, would hit the surface of the plant and potentially could stay there based, I mean, obviously you always want to wash your vegetables, fruits and vegetables before you eat them. And so this is where 60% of participants water plants were the harvesting rainwater from top down. And so we would advocate that we would want to be irrigating the crops at the soil level. We saw E. coli presence and absence in harvesting rainwater was not associated with the presence and absence in the soil, meaning that there was not a connection between the two. All right, now we're going to go on to pesticides. And so we studied a lot of things. So I'm going to kind of go through these and make sure we have enough time for questions. This is where we looked at pesticides and industrial compounds. Here's a list. Don't get caught up in too much of this. Just acknowledge that we have pesticides and industrial compounds. For the organic compounds, we're going to be reporting back in nanograms per liter. So this is looking at parts per trillion. So this would be the equivalent of a drop of ink in 12 million gallons, or 18 Olympic-sized swimming pools. Okay, so parts per trillion, very small concentration. All right, so if we look here, what we see in this figure is that this is giving us the mean or the average concentration of combining all years together. The number above each bar is the number of detections. So it's very important to talk about that because we did not always detect these contaminants every sampling period. What you can see is most compounds have a mean concentration at or below 50 nanograms per liter, except for simazine, the perfluorinated, these PFOS and PFOA, which are perfluorinated compounds, are closer to 100 nanograms per liter. Nonylphenol concentrations were above 250 nanograms per liter and had the highest mean across all communities for all years. What is nonylphenol? So nonylphenol is a surfactant with wide industrial uses, right? So it's also used as an inert or non-active ingredient in pesticide sprays and has been known to travel long distances from the point of application. So when we looked at what was most frequently detected in terms of these pesticides and industrial compounds, you can see that this was the highest mean concentration. Here we're looking at frequency of detection. So the number of times we had a measurement above the limit of detection of the instrument. You can see that it's prometon, nonylphenol, petrochlorophenol, and then PFOS. Again, I'm just showing you some data and let's take a couple minutes to look at this. So this is now showing mean concentrations by community for all years in nanograms per liter, but now you're seeing it divided out by community. And so now again, remember that this value above each bar indicates the number of detections out of 595. We can see here petrochlorophenol, right? This is a fungicide, interestingly widely used to treat utility poles and railroad ties. So this is to reduce pests in the utility poles that we have throughout our state. We can see here that Globe Miami had a little bit of a higher mean when compared to others. We see prometon, which is an herbicide that's used on bare ground, around buildings, on fences, and can be combined with asphalt, which is crazy, and applied in or below roads and in parking lots. High concentrations could be expected during application time, but harvested rainwater systems near roads and parking lots might be impacted. If we look at this group, we see these are the greater mean concentrations of industrial compounds. In general, concentrations were greater in Tucson, followed by Dewey Humboldt. So when you look at these all together, and then Globe Miami, Hayden Winkleman, and I'm just highlighting here, right, which is looking at like these perfluorinated compounds. You can see Tucson had a higher mean value and detection number for PFOA. If we look at PFOS, we see that all communities have a slightly similar mean value. And then for PFBS, we see that actually this was Globe Miami, which just, highlighting these differences in these mean concentrations by community. This is looking at rural versus urban. So now you can see here in the legend, we're now dividing out the data still by analyte, but now we're looking at, is there differences between population density? Again, the number above each bar is the number of detections. And the bold indicates that a statistically significant difference was observed. So we did see significant differences in what you see bolded here. Nonylphenol concentrations were greatest in Tucson, and its frequency of occurrence. And concentrations were greater in rural locations for prometon, carbile, and simazine, which are all herbicides, but the frequency of occurrence was higher in Tucson at lesser concentrations. So you can see we're kind of going back and forth of like, what is the greatest, but then when was it detected over the years? And so as I started to talk about when looking through some of the, looking through the data with the organics, we saw pesticides were greatest in rural concentrations, but the frequency of occurrence was greater in Tucson, but at lesser concentrations. We saw that these pesticides, Petrochlorophenol, as well as Promoton and Simazine concentrations were greatest in the monsoon sampling. This is something that in the summary of slides for arsenic and lead, I kind of glazed over quickly, which we can come back to, is looking at season. And when we think about the industrial compounds, we can see here that nonylphenol concentration was significantly lower in monsoon, but the frequency of occurrence was higher in winter, and at greater concentrations. This perfluorinated compound, industrial surfactant, which is used in nonstick cookware, water repellent clothing, mean concentrations were greater in rural communities, greatest in Globe, Miami. But again, the frequency of occurrence was in Tucson, was higher in Tucson, but a lower mean concentration. And PFOA was greatest in Tucson, and so was the frequency of occurrence. So compounds like these perfluorinated compounds, which are called considered persistent organic compounds, have been measured in rainwater in regions with no direct sources, meaning that we know that these are an issue globally and can be detected in areas that aren't right next to a point source. We did see when we compare a risk-based non-enforceable drinking water standard, when we compare these perfluorinated to, we can see that we had 57 exceedances in their harvested rainwater. So 57 times there was a value, combined value of these together were greater than 70 nanograms per liter. Carbile does not had a standard of 0, and we measured 122 exceedances of the partial body standard for surface water. And so just as I'm doing today of disseminating the information, we've done a variety of ways to share the information with the participants and families. So between 2018 and 2021, we hosted 5 data sharing experiences called Ripple Effect. You can see here, this is a, essentially the data is transmitted into sound waves, and we have a tray of water that vibrates and shows the more vibration, the higher the concentration. And if a light goes off, that means it exceeded a standard. We did 5 of those in English and 5 in Spanish. We did 5 English and Spanish booklet only sharing. So again, going back that this was a learning research grant, we were trying to tease out differences in kit design and also in how people receive their data. And so half the families first year would just get a booklet, the other half would get a booklet and Ripple Effect, and then they'd switch. And then at the end of the project, everyone got both activities. We've also built an interactive bilingual website, interactive bilingual map, are building a massive database. And we've also had ongoing communication through external advisory boards, internal advisory boards, and provided quarterly updates at different community. In this case, this is an environmental board, and these are Superfund. This is an alternative Superfund site multi-org call. And I'm also giving presentations at county levels like we did today. So in summary, we have a tremendous amount of data. What I showed today is just a snapshot. Overall sampling season and community characteristics influenced contaminant concentrations. And so stay tuned. We're working on generating a summary of results, providing more social media highlights, and making all the audio recordings and additional public presentations available. And we also are employing fair data management practices and hope to we'll have an open access database to all the de-identified data sets. So thank you all so very much for your time today.
Yes, thank you so much, Monica, for Dr. Ramírez Andreotta for speaking with us. And we so appreciate all of your hard work, and your voice is very soothing. I don't know if that's a thing, but I was like, oh, you sound so nice, even though it was, you kept a good pace, and I enjoyed listening to you speak. And I felt like you presented the information very clearly And I was impressed with your presentation. So thank you so much for sharing your work with us.
Of
Agree with
course.
Alex.
Thank you. I appreciate that.
You can contact me at alexcosmiter@arizona.edu. And there is a plethora of information available on our website. And if you have any questions for Dr. Ramirez Andreotta, I'd be happy to forward them on to her. All right, thank you guys so much for coming, and I hope you have a fabulous afternoon. If
Thank
there
you,
are no
everyone.
questions.
Thank you. Bye-bye.
Bye.
Thank you. Take care.